Testing, testing, hey, testing. All right. And then on, off. Test. Go ahead. Testing, testing. All right. My mic works.
Being tested. Oh, yes, I work too. All right, we worked through all the technical difficulties. That's what that last 5 minutes before any program is for, right? All right, well, good evening, everyone. I'm Dr. Billy Teets, and I'm the director here at the Vanderbilt Dyer Observatory, and it is my pleasure to welcome you to our September 2025 Meet the Astronomer lecture. So thank you all for being here this evening. We are also live streaming to YouTube, got the camera back there, and as folks have questions from afar, make sure that you put those questions in the chat as we're going through the talk. Let's see. I just want to take a couple minutes to tell you about Dyer Observatory. But first of all, how many people are up here for the first time? All right, so that's kind of the trend that we see at every event. We've got a lot of returning visitors, which we love, but we also have a lot of new people coming as well. So I just want to give you a little info about the observatory. So we are dedicated to expanding our educational and our programming outreach in the community, into schools, and basically all over the globe. So we've been working hard this year to improve our facilities, improve this site, make it even more unique than it is. So we are also dedicated to trying to expand our educational outreach. So one of the things that we're working on is fundraising for an inflatable planetarium that not only would we be able to use up here, we'd be able to take it out into the community, we'd be able to take it out to schools. So, it would be a boon for us. And, things like that, of course, that costs money. We rely heavily on, fantastic folks like you all to help us, chip in and pay for that. So if you'd like to make a donation to us, we've got QR codes posted around the observatory, and there's on our website a place where you can chip in a donation there. So also keep an eye out on our website and our social media for upcoming events. I'll highlight just a few of them here. Tomorrow, we have the Latin Jazz Ensemble from the Vanderbilt Blair School coming up. They're actually going to be doing an hour-and-a-half concert up here. And Latin jazz is not complete unless you've got dancing. So anybody like to dance in here? Don't be shy. Yeah. Okay. Anybody not able to dance? Don't be shy. Okay. Well, if you can't dance, but you're maybe interested, we got you covered because we do have tickets still available. And that ticket includes an hour dance lesson, a group dance lesson. So you're not like one-on-one, but so it is Amanda Ewing of Salsa Soul Nashville will be up here. And she's got a big group that's going to be that she's going to be teaching. She's got a few other dancers coming up to help out as well. So you'll get a little education, then you'll be able to go out and dance the night away with the Latin Jazz Ensemble. Next Thursday we have another talk, and actually this talk was supposed to have happened back in April, and that was the period when we had those like 1 or 2 days of tornadic weather. I had like 3 or 4 tornado warnings I had to go through, and the folks that were actually visiting from Greece and from Mexico that were going to do this talk, they weren't able to do the talk because they were having to shelter in their hotel kitchens like several times during that period. So they didn't get to come out here during their visit, but they got to make it out to a lot of different organizations, including some schools in the area. So we're doing a makeup talk. So they're obviously not going to be able to be here, but they're going to join us virtually, and we're going to have an in-person talk here. They're going to do the hour talk about the Antikythera mechanism. And if you don't know what that is, I'm not going to tell you. You'll have to come see the talk.
I don't know what that is.
But afterwards, we're going to do a little bit of extended telescope viewing if it's clear. So we've still got tickets available for that as well. We are approaching a wait list, so get them now. Let's see, October and November, we have 2 other Meet the Astronomer talks lined up with Professor Emeritus of Astronomy, Dr. David Weintraub. I'm actually my PhD advisor. And then a brand new minted PhD, Jessica Schoenhardt-Stasek. So she'll be coming up to finish up the year with our lectures. October 18th is our last Bluebird on the Mountain concert, and there are a few tickets available for that, so grab those while they're available. And then if you're ever interested in a really cool rental venue, we do rent out the place. So you can come chat with me, check out our website, you can get more information about that. So the program for tonight, first of all, I want to send out a huge shout out to the Vanderbilt University Department of Physics and Astronomy because they helped co-fund this particular event so that we could have a little bubbly, non-alcoholic bubbly that is, a little cake as well. We've never had cake at an astronomer lecture in the history that I've been here. I think this is a brand new trend. So a huge thank you to them for helping to support all of that. The talk will go for about 45 to 60 minutes. We will then open the floor to a Q&A session afterwards, so please hold your questions. And again, those that are watching on YouTube, go ahead and put your questions in the chat, and we will get to those questions at the end as well. And then afterward, if the skies clear up, you can go up to the Seifert telescope and check out Saturn. Even on a partly cloudy night, Saturn can usually be seen through the clouds, but even if it is too cloudy, especially if it's your first time here, go up and check out the telescope. It's really, really cool. So tonight, our presenter, our returning presenter, is soon to be Dr. Bill Smith. So PhD candidate Bill Smith is an astronomy graduate student whose research uses gravitational wave observations and hydrodynamic simulations to better understand the universe's origins and evolution. Most black hole mergers only produce gravitational waves without their electromagnetic counterparts, making cosmological inference challenging. But crafty statistical models have been developed to extract astronomical and cosmological data by associating gravitational wave signals with galaxy catalogs. Bill's research uses hydrodynamic simulations to test and advance these methods. And besides doing science, Bill loves thinking about people, societies, and cultures doing science and how to make the scientific community more welcoming, supportive, and communal. So with that, I will turn the mic over to him, and you're going to be wowed. He's a fantastic presenter. I mean, this is his fourth time here, and yeah, he usually is asked back immediately. So without further ado, let me turn it over to soon-to-be Dr. Bill Smith.
Thanks, Billy.
Okay.
Yeah, am I coming through on the mic? Yes. Okay. Yeah, I was telling Billy, so when you get your PhD, you have to go through this process where you have a committee, and that committee is essentially a group of professors who look at the work you've done and give you some very, let's say, comprehensive feedback and essentially tell you if and when you're ready to graduate. And I had a meeting with that committee on Monday, and they said, we think you're ready to start defending in the spring. And that meeting was way more nerve-wracking than this one is. So when they say soon-to-be doctor, it's a little peek behind the curtain. So yeah, as Billy said, my name's Bill. I'm a fifth-year graduate student. I work broadly in a field called gravitational wave cosmology. Tonight, I'm going to be focusing on the gravitational wave side of that, but if you want to talk about the cosmology side, I'm always down. Feel free to grab me after the talk and we can chat cosmology. The other thing I wanted to say, if you haven't had a chance, as Billy mentioned, we have some bubbly. We also have some cake afterwards. I just wanted to have a party tonight, y'all. You know, like these talks are great. You all come. I talk about mind-blowing things. You all learn a lot. That's all well and good, but I just wanted to add a little bit of icing to that tonight. So just to start out, I was inspired to give this talk by this gentleman in terms of, you know, the title and getting some entertainment vibes. If you don't know who that is, ask someone older and make them feel old. So today we are here to talk about this one event called GW150914, and that's a little bit of a mouthful. So I wanted to, before we dive into some details, just break that little piece down for you. So the GW stands for gravitational wave. Probably not that surprising after the introduction you heard. But the number, it's just a date. It just tells you when that gravitational wave event was observed. So this particular one was observed on the 9th month, the 14th day of the 9th month of the 15th year, which, if you think about it, was almost exactly 10 years ago to today. So here we are. So cheers, everybody. I wanted Bring some bubbly. If you have some bubbly, please raise your glass. Cheers to 10 years of gravitational waves. I was originally thinking about making my entire talk the cheers and seeing how long I could keep you all holding your glasses up. But I decided to be a little nicer than that. So basically, I want to spend this talk talking about what we just cheersed. So we are celebrating the 10th anniversary of looking at the universe with a brand new sense. So senses, seeing, hearing, tasting, touch. Not only do we use those to understand the room we're in and the sensations around us, but we use them for the entire universe. We understand the universe through light. We understand the universe through particles. And now we understand the universe through these things called gravitational waves. And so just a primer on the non-gravitational wave universe. We have this thing called the electromagnetic spectrum, light. There's a bright one shining in my face right there. We have these lovely organs called eyes. They have these photoreceptors that measure this light, tells us about the environment around us. And we developed some lovely instruments to augment our ability to see the universe through light. This is a lovely fellow Galileo a few hundred years ago who was very famous for doing this. Today, our instruments are a little more advanced. I imagine some of you came here today because you can check out that really cool toy upstairs after this. And so where we're at in terms of seeing the universe through light is essentially here. We know that light has this spectrum. Our eyes are sensitive to a tiny little part of it, which we call the optical part. Since then, we've built all these cool devices that can see other parts of the spectrum. Some of them we have to put into space because the atmosphere blocks some of that light. And we learn all these cool things about the universe. In addition to light, we've also learned to see, feel the universe through particles. I'm not going to go too much into detail. This is like a topic for a whole nother talk. Essentially, the red on there, those are protons, really, really high energy, fast moving protons that things in the universe give off. They hit the Earth, we can measure them. The green ones are these things called neutrinos. You may have heard them called a ghost particle. They're very light, they don't interact with much. Neutrino science is a whole other branch of astronomy. They also tell us about the universe. And then there's this third one, gravitational waves, which is what the entire rest of the talk is about. And so just to give you a sense of how we've been able to understand the universe through these senses, we've been able to observe our universe through light since we have been able to look up. So all of human history. Particles, we've been able to feel the universe. We've been able to feel the universe for about a century, and gravitational waves almost exactly 10 years. And so this is our brand new sense, and it has revolutionized astronomy. So what are gravitational waves? To understand what a gravitational wave is, first, we have to understand what gravity is. So who recognizes that gentleman, or at least the cartoon? And someone shouted out, who Newton, yes. So most of you are probably familiar with the story of Isaac Newton, one of the most famous physicists in all of human history. The standard story is he was sitting under an apple tree, got bonked on the head. He was thinking about problems like, maybe it's the same thing that pulls an apple from a tree to the earth as holds the moon in orbit around the sun. And so he came up with this theory. It worked really, really well. And that theory essentially said things have mass and things are separated by a distance. We can figure out how much they attract each other based on how heavy they are and how far away they are. And that theory worked really well. It described how the apples fell. It described how the moon went around the Earth. It described a whole bunch of other things like cannonballs flying, and engineering had a huge leap forward, and everything was all well and good. But then, does anyone recognize that dapper young gentleman? Einstein. Does anyone know how old Einstein was in this picture by chance? 26. Yes, 26. Bingo. This is Einstein at the ripe old age of 26. Man, 26 looked a lot different in 1905. So in 1905, Albert Einstein was thinking about Newton's theories, and these theories had a few quirks that were starting to come out. People were starting to question it. You know, it had worked amazingly. One of them was this idea of spooky action at a distance. And this was the phrase that they used for this since Isaac Newton's time. In fact, other scientists came to Isaac Newton with this thing called spooky action at a distance. It really bothered a lot of physicists, and the idea was, let's say the Earth is going around the sun, right? We have mass, distance, gravity, great. What happens if the sun just magically disappeared? Would the Earth just instantly start flying off with no time passing, or would there be some kind of delay time between when the sun disappeared and when the Earth felt the gravitational effect of that disappearance, right? Because it seemed really weird to them that this force of gravity was exactly instantaneous, that right here, I could do something that could affect the movement of something halfway across the universe. And they called that spooky action at a distance. They didn't like it. So that was an issue. Additionally, there was this guy named James Clerk Maxwell who said that the speed of light is a constant, and that doesn't line up with Newtonian mechanics. And then they also noticed that Mercury was doing some weird things. Mercury's orbit wasn't lining up exactly with Newtonian mechanics. If you ever heard of a planet called Vulcan, there was this theorized planet that was kind of invented to fix this problem with Mercury's orbit. They never found Vulcan, and so Mercury's orbit was still screwed up, and they didn't know why. And so Einstein was thinking about all these things, and he came up with a new theory, and he said gravity isn't actually a force, it's geometry. So there's a very famous saying by a guy named John Wheeler to describe Einstein's theory, the theory of relativity, and that saying is, matter tells space-time how to bend, and space-time tells matter how to move. So you can kind of think of it like this little GIF. I'm a hard G GIF guy. This GIF, you have some mass. It's in this space, this geometry. As it moves through that space, it bends that space. As that space bends, it shows the object how to move. So they usually tell us not to put equations into public talks. They're scary. I spared you from the Newtonian mechanics equations. Those are very annoying, but I figured I would break that tradition and give you all a quick lesson in general relativity. So I think you all can handle it. Let's go for a general relativity lesson together. I'm going to give you a year's worth of GR in like 30 seconds. So this is the Einstein field equation. This term tells us how space-time curves. That term tells us how matter moves. That's just some numbers and junk. General relativity. Congratulations. So you might be wondering, looking at that equation, why does that warrant a year of graduate studies? And the real devil in the details are those two little subscripts that you see on the G and the T. That's where all the scary horror lives. So if you ignore that part of it and just look at it this way, that's general relativity. So that's what Einstein said. So how do we get from gravity to a gravitational wave? So we have this new theory, and Einstein and some of his buddies were saying to themselves, okay, we have this model with mass and this geometry. Is there some sort of scenario or setup where that space-time itself can ripple like a wave? And they did some calculations and some toy models, and they came up with the conclusion that, well, in theory, these ripples could exist. We're probably never going to be able to detect them. And what they basically learned was that for these waves to exist, mass has to accelerate. And so, if you're in your car driving down the highway at a constant speed, you're not making a gravitational wave. If you slam on the brakes, you made a gravitational wave. Congratulations. The other thing they realized was that you need a ridiculous amount of mass to create a very tiny wave. And so much mass and such a tiny wave that it's actually incredibly hard to conceptualize. So this is where we actually get into the astronomy side of it. This is a diagram of different stars, how they live, how they die. So if you have a normal star like our sun, you can think of that as like one in the top left there. Our sun's a pretty average star. When the sun runs out of fuel and ends its life, it's going to become this thing called a white dwarf, a small, compact object. A more massive star than the sun is going to end up on this middle track, which we call a neutron star, and the most massive stars are going to become black holes. And to give you a sense of how dense and how massive they are, this is an actual to scale rendering of what a neutron star would look like hanging out above Queens. And that neutron star would be probably 3 or 4 times as massive as the sun at that actual size. So that's the kind of extreme density we're talking about when we're talking about objects that make gravitational waves. So they said to themselves, okay, we have this dense thing. It needs to now accelerate. How can they do that out in space? Well, if you have 2 of them in a binary orbit like that, theoretically they would make these ripples, gravitational waves. So that's the setup. That's where we got GW150914. So I have a video here to give you a scale. It has been one of the biggest challenges of my PhD just to wrap my head around the scales that we talk about in astronomy every day. This is my best attempt to convey it to you. So this is a video that will show you the sense of scale in astronomy. So we're starting here at our normal old earthly self, and this is going to zoom out for like a minute or 2. Let's see. Yeah, I think this was taken at the Googleplex, so you'll see San Francisco. And if you're a fan of Google Maps like me, I can spend a whole afternoon just like looking at the maps. They're so beautiful. Now we're getting into the regime that most people think of when they think of astronomy. Solar system dynamics, Earth, Moon, Sun, planets, things like that. We're still at a distance scale. Actually, the bar is covering the distance scale, but we're like at 1 billion kilometers now. Unfortunately, I have to keep the bar up because I memorized the exact time step that I have to stop this because I did some math that I want to tell you about at that time step. So now we're at a scale on light years, hundreds of light years. You're starting to see some of the stars in our local neighborhood. All right, now we are at the Milky Way, which is about 100,000 light years across. And yes, we are not at that timestamp yet. This is how big we think in gravitational wave world. So we are right, oh, let me pause it right about there. Yeah, that's my timestamp. So this is where what we call the cosmic web, billions of galaxies, start to look uniform. And sorry, it looks like, let me see if I can unblur that a little bit. If it's going to render, yeah. So right about there. So this is the cosmic web. Each of those little dots is a galaxy. And what I did is I did the math to figure out at that scale how many of these gravitational wave mergers would you see in the universe. So this is the actual rate. So if you look closely, it's a little hard to see, but there are these 2 black dots. There's about 20 of them on there. We see about 20 mergers per year in that exact volume of space. Huge amount of volume, 20 per year. That's the actual astrophysical rate at the scale of the universe. So that's what we're talking about when we actually see these things. And now if we play the video again, will hit our universe scale. Now we're going to zoom back in, and once we get back to Palo Alto, we're going to go the other way and go atomic. All right, we're back to Earth. All right, now we're going to go really small. The nice thing about physics is we never think about things on a normal scale. It's always super big or super small. Anything in between is for another degree. All right, now we're getting subchromosome. I'm so glad I have bio friends to learn all this because it's really hard. All right, so this is about the size of an atom. An atom is mostly empty space. And now we are coming in on the nucleus. And if we pause it right there. All right, so these are the particles that make up protons. They're called quarks. When one of those mergers happens at that huge scale, there's two lines there, not one. That is about how much space-time displacement a gravitational wave from one of those sources makes. This is the smallest distance I could render on my program. Doing the actual math, those two lines should be about 1/200th of the distance of that arrow. That is the actual space-time scale that the gravitational wave itself makes from one of those mergers. So I hope that helps you get a sense of what these things are. So now we have this picture where these things merge. They create these ripples. This, I'm glad they put vastly exaggerated. They shake the Earth. And as we saw, this is not an insignificant fraction of the observable universe. So that's the overall picture of gravitational waves. So, coming back to Earth. Gravitational wave hits the Earth, shakes it, and we built these two detectors. We call them LIGO. LIGO stands for the Laser Interferometer Gravitational Wave Observatory. They can detect these wiggles. One of them is in Louisiana, a little town called Livingston. It's outside of Baton Rouge. And then the other one is in a place called Hanford, Washington, in the Pacific Northwest. And they look like that. Those are the actual pictures. Each of those tubes is 4 kilometers long, and they are vacuum. There is no air. Those are the largest vacuum tubes we've ever created as a species. And so you might be asking yourself, well, what do those detectors actually do? How do they measure these waves? So what we do is we shine a laser, we split it, and we send part of the laser down one of the tubes, part of the laser down the other tube. They hit mirrors, and they bounce back, and they recombine. If there's no wiggle, they recombine in such a way that the light cancels out perfectly, and you don't see anything on the detector. But if one of the arms shrinks or stretches just a little bit, now the light doesn't perfectly interfere and you get a signal. And we can build lasers with enough precision that we can measure that wiggle on the scale of a 400th of a proton diameter. So that's what we've done as a species. Isn't that amazing? Yeah, it's unbelievable. So it sounds simple. This is what a more advanced schematic looks like. I am not an optics person. I don't know how that works. I do the astrophysics. There's a whole team of engineers who are way smarter than me that actually build and maintain it. But that if you're more of an engineer or an optical person, that's for you. And so the first one we detected was in 2015, but this was actually a much longer time coming. So we talked about Einstein earlier. Einstein laid out a lot of this theory in 1900s, 19-teens. For decades, physicists just assumed that we would never be able to detect these wiggles. It's just too hard engineering. I showed you the scale. You can imagine people 50 years looking at that math and being like, too hard. But in the late 70s, academics do what they do. And some folks at MIT and Caltech said, we think we might be able to do this. And the NSF said, what? Okay, we'll give you a little money. We think you're a little crazy, but give it a try. In 1984, they formed this LIGO collaboration officially, and the detectors were constructed in the early 90s. So right off the bat, you can see how long of a process something like this takes from idea to reality. The first interferometer started, so by the way, interferometry, we call that L-shaped two-laser thing an interferometer. It's a very fancy word. Interferometer is just a fancy word for L-shaped laser device. So they achieved their actual initial design early 2000s. They had this whole initial run for the first decade of the 2000s where they actually were running, but they didn't find a signal. But they knew enough about gravitational waves that they weren't expecting to necessarily find a signal. If they did, they would have been actually very surprised. So it wasn't like a, death knell, oh no, woe is us kind of thing. Like they concluded and they're like, we didn't find anything. We didn't expect to find anything. We're cool. But the reason they weren't panicked was because they had an idea for this more advanced design, which started running in 2014. And then less than a year later, we actually got that first detection, which is why we're here tonight, GW150914. So, they did the thing that you do when you make a detection like this. Is there a...
We have detected gravitational waves. We did it.
So that's David Reitz. He was the director of LIGO at the time. Hit the timing really right. He got to give that talk, got to say that at the NSF. That would have been in February 2016. And then, of course, we got all the headlines, the New York Times, BBC started reporting on it. It was a great day for science. This was the paper. The paper came out the following February. The detection was made in September of 2015, and then once they actually detect it, takes time to write it up, make sure they did everything right, send the paper out. The actual paper was published on February 11th of 2016, so that's the day the world found out. And I actually looked this up right before this talk. That paper, in about a decade, just under a decade, has gotten over 12,000 citations. And to give you a sense of citation counts, I also looked up what the most cited papers in astronomy in every other year for the last 20 years was. The average was around 2,000. So you can get a sense of just how important this paper was in science history. And so now we can talk a little bit about the event itself. So it was detected at both detectors, Hanford and Livingston. One of the reasons you have two detectors is because for something that's sensitive, if you detect it in both, you can be more confident that it's not like a truck driving by or a hunter. Actually, at Livingston, fun fact, they do have issues with hunters and their rifles making vibrations that set off the detector. So they know if they measure it at Hanford, it's not the Livingston guys' rifles. So this is a little audio clip of what the detection actually would sound like in the detector. The first one is the raw signal, that lower rumble. The higher one is the cleaned data. So I can play it again. And in the gravitational wave world, we call that whoop sound a chirp. So if you ever hear people talking about the chirp, oh, what's up? Yeah. How's that? can also try doing it with my voice too. All right, I'm at max. This is as high as it goes. Oh, boop.
Ladies and gentlemen.
Can hear David again. All right, one more time. Contact? Okay. Well, actually, we'll be mentioning interstellar a little later, so. All right, so that was the sound. You can actually take these gravitational waves, translate them into a sound, and listen to them. And if you break down the wave a little bit more, they have these three phases. So the first phase we call the in-spiral, and you can think of this as the part where the two objects are orbiting each other really, really fast. They haven't combined yet, but they're about to. And so you get this very periodic, kind of sinusoidal, if you know that word, signal. And then right as they merge, you get this drop in, or the frequency shoots up. So this, if you turn it into a sound wave, it goes boop, and the pitch goes up. And that's when they're actually merging. And we call that the merger. Creative, I know. And then after they merge, you have this piece called the ring down. And the ring down is essentially when they merge, they're these two spheroidal objects, but they have a little bit of asymmetry, even though they've kind of become one object. And as they spin, that asymmetry kind of wobbles out a little bit, and it becomes a new circular object. And we call that the ring down. Fun fact, in our department at Vanderbilt, every Friday from 4 to 5, we also have an event called Ring Down, where we hang out and just chat about our week and have like a drink or two. So if you ever wonder why we call it Ring Down, that's where it came from. You're all probably welcome to come. We're not going to say no. So just getting to know the merger itself a little bit. So in LIGO world, we refer to the detectors as L1 and H1 for Livingston and Hanford, so that's what the L1 and the H1 means. We know that these were black hole sources, and we have the exact time. I think in Central Time it was about 2 in the morning when the signal actually happened. These numbers just tell us how sure we are that it was a signal. Probably the one that would make the most sense is the bottom one. That's called the false alarm rate. And essentially what that means is that is how long we would expect to look at our signal or look at our stream of data where there's no signal and expect to see this just by chance. So our false alarm rate of 1 in 200,000 years means, yeah, we would expect to have our machine on for 200,000 years straight, and one time in that time we would expect to see a signal like this just by chance instead of it being an actual real event. How far away was it? So the top numbers are in light years. If you're familiar with the unit of a light year, the nearest star is like a few light years away. The G in front of the light year stands for giga, which in science means billion. So it was about 122 billion light years away, which for us is on a cosmic scale. It was not in one of our local neighbor galaxies. We know about what the masses were. So the primary and secondary mass, those are the masses of the two black holes before they merge, about 30 to 40, 20 to 30 times the mass of the sun for each one separately. And then once they merge, we call that the remnant. You have one new black hole that's more massive, and we know that was about 58 to 67 solar masses. And for those of you that are paying some keen attention, you'll know that the bottom numbers are actually a little less than if you would add up the top numbers. Because gravitational waves give off energy. This is actually one of my favorite gravitational wave facts. When you have a gravitational wave merger like this, usually in the merger, they will give off like 2 to 3 solar masses worth of energy in gravitational waves. So if you think of like E equals mc square, mass is equal to energy, imagine like multiple suns dissipating in gravitational wave energy. And actually in that moment, when they merge, they are giving off more energy than the entire rest of the universe combined for like a little split second. It's a massive, massive amount of energy. And then how much human power did we have to put into analyzing this data and getting this done? For those of you in the computer world, the analysis took about 50 million CPU hours. And there were 13 scientific papers that were published on the day that we call it an embargo, the day we're allowed to talk about the event. And then the number of researchers, about 1,000 people over 80 countries and about 80 institutions in 15 countries. So this is a worldwide scientific undertaking. The next year, these three gentlemen were awarded the Nobel Prize. So you're all probably familiar with the Nobel Prize in general. This one is special because usually when Nobel Prizes are awarded, there's a little bit of a delay between when the science happens and when people are awarded the Nobel Prize. Usually it's like some decades. The papers came out in February of 2016. What year is that? 2017. This was one of the, if not the quickest turnarounds between when the scientific discovery happened and when the Nobel Prize was awarded for the discovery. It was like an instant Nobel Prize level discovery. So the guy on the left is Ray Weiss, who actually passed away just over a month ago at the age of 93. We actually learned about his passing like the day before, some stuff I'm going to talk about later, so it was very momentous for our collaboration. That's a picture of him as he would probably like to be remembered at MIT, next to a sign that his group installed, warning some passing cars of black holes. So the guy on the right is Kip Thorne, who's probably the most well-known of the three. Kip is kind of a cult figure in physics. A lot of us within the field have, Kip stories of when they met Kip or talked to Kip, and it's just kind of a badge of honor. Most of you would probably know of him because after he became super big in the scientific world, he decided to have some fun outside of the scientific world and did a lot of work in Hollywood advising movie writers and things, and he was one of the main people who advised all the folks making Interstellar about their science. So if you've all seen Interstellar, for those of you that have, and you're like, man, those effects were really cool, how did they do that? That was Kip. And then the last one is Barry Barish, who is probably the least well-known of the three, but he's noteworthy to me because he's the only one of the three that I have met personally. He gave a talk at Vanderbilt in 2019, and I got to chat with him for an hour, and he was very, very lovely, very nice. I've always told people that my ideal level of fame would be Nobel Prize fame, because you can walk into a specific room of specific people who think you're just the most amazing human ever, and then you can leave the room and walk into a restaurant or a grocery store and nobody knows you have a Nobel Prize. So yeah, it's kind of neat. Yeah. So I mentioned LIGO. Currently, we have what I call the full LVK, the LVK collaboration. In addition to our two detectors in the United States, there's now a detector in Italy called Virgo, which I am hoping to, and many of us are hoping to visit. There's one that just opened in Japan called Kagra. That one is actually underground, which is really cool. It's hard to build one of these in general. It's really hard to build one of these underground. So if you ever hear the LVK in reference to gravitational waves, that stands for LIGO, Virgo, Kagra, and that is our full detector network on Earth at the present day. And currently they're building a new detector in India called LIGO India. Here is a rendering of what they're expecting it to look like. And I actually have a photo here because the guy who is the second to the left, sort of in the back with the black suit coat on, that's my advisor at Vanderbilt. This was taken in 2016. And that is him next to the Prime Minister of India when they signed the contracts and MOUs and everything to use LIGO technology to build a detector in India. And I'm sure he would be thrilled that I put this picture in there. So, And in terms of the total collaboration, this is what the people power looks like. I am in that picture somewhere. This is in a little hotel lobby area in Barcelona. This is about a quarter of the LVK collaboration. So the total number of people, if you copy and paste that like 3 more times, that's how many people are actually involved in these detectors and doing all of this science. And here is a picture of all the institutions worldwide that are involved in the collaboration. So it is worldwide humanity level science at this point. So breaking down the LVK a little bit more, when we turn on our detectors, we divide our time into what we call observing runs. The detectors can't be on like all the time indefinitely. We have to turn them off sometimes, do maintenance, make them more advanced, do some upgrades, things like that. So when you see things like 01, 02, 03, that just says observing run. You know, the first one, which was our first discovery, happened in late 2015, and that's the little orange. The numbers up there tell you about how far into the universe we could see for that observing run. So that unit, MPC, stands for megaparsec. 1 parsec is about 3 light years. So if you know light years, just multiply it by 3 and you have a parsec. The M stands for mega, which is a million in science world. So if you see 100 megaparsecs, that is about 300 times a million, or 300 million light years, which again, the closest star is like a light year. Closest galaxies about 3 million light years away. So that's the scale that we're seeing things. So we had 01, we had 02 in like 2017, 2018. We had 03 in 2019 into 2020. 03 stopped due to some other things that were going on in the world in early 2020. It was supposed to go a little longer, but we had to cut it off because we all were quarantined suddenly. But we still got a lot of really good science out of it. So this is a visual of each of the chirps of all of the gravitational wave signals through the third observing run. So we got very lucky actually, because our first one, the one we've been talking about, was actually pretty loud. You'll notice that it's a pretty intense signal compared to some of the other ones. So it came through loud and clear. The color coding is the observing run. So the first 3 like greenish blue are from the first observing run. The red ones are from the second observing run, and the purple-ish is the third observing run. So you can see as our observing runs have gone on, we've gotten a lot better at detecting these. The reason we've been getting so many more of them is because the distance our detector can see has been going up for each observing run. When that distance goes up, that increases the volume, and when you increase the volume, you get more volume to see these detections. This is a visualization of the actual events through the third observing run. So the way to think about this, we can see black holes and neutron stars through a couple of different ways. You can see some black holes through the X-ray emissions that gas going around them gives off. We can see those through telescopes. So those are represented by red in this picture. We can also see neutron stars through the light that they give off, and those are represented by the yellow. The objects that we have seen through LIGO are represented by the blue and the orange. So the orange are the neutron stars we've seen in gravitational waves. The blue are the black holes we've seen in gravitational waves. And so essentially we have all of the original black holes that merge. There's 2 of them, and they merge into one new remnant black hole. That's what the arrows mean. So for each one of those events, you'll see like 2 black holes sort of stacked, and then there'll be an arrow pointing to a third one above it. So that tells you how massive each of the objects were on that far axis on the left over there where it says solar masses. That's how much each of these objects weighed. So you can get a sense, we're seeing things that we just cannot see with light. So that's up through the third observing run. You all are here at a great time because I actually didn't show you the full plot earlier for observing runs. I only showed you through 03. This is what the rest of it looks like. We are currently in the 4th observing run right now. We actually broke it up into 3 different sections. We had breaks where those little gray areas are. So the first one we actually call O4A, second one we call O4B, the third one we call O4C, and O4C is actually still ongoing for the next few weeks. So we are still taking data, and you'll notice above the purple O4, our distance is bigger than in prior observing runs. So I have some treats for you because 01 through 03 has been public for years. The 04 data became public on August 26th, 2025, which is actually the day after Ray passed. So it was a very high emotionally charged day for me at LIGO because, fun fact, in addition to doing the science, I'm also on like the press and outreach team because we have to like write press releases and talk to the New York Times and all of that. So we were managing all of the news articles that were going out about the data that we knew were coming, and then we found out about the passing, and we were just like, this is both emotional and labor whiplash for us. So that was quite a week. So this was the paper for 04. We found 128 new objects, which means our new catalog now has 218 candidates. And so me and Ryan, who's a graduate student at Vanderbilt, and Karan, who's a faculty member at Vanderbilt, made the new plot. So what I showed you before was just that top chunk through 03. Just in 04, we have more than doubled the number of objects that we have found. And here's what, snap, that's awesome. And this is what the updated merger plot looks like. Actually, I was at a colloquium this afternoon on campus, and the person giving that colloquium called this the Deadly Raven plot, because he actually had this plot in his talk too to our department. And so I might adopt that. This is what the updated Deadly Raven plot looks like. And now we're starting to get into some plots that look a little more technical. Don't let it scare you. I promise. I'll hold hands. So this is essentially the mass ratio of our objects. So on the bottom axis, you have the mass of one of the objects, and then on the other axis, you have the mass of the other object. The blue ones are all of the ones we found in the most recent run. One of the things that is the most noteworthy is we didn't expect our distribution to be this massive. When LIGO was founded and all of the astronomers were studying stellar deaths, they were expecting a lot of these black holes to be in that like 5 to 10 to 20 range. And what we're finding now is that they're in this like 30 to 50 to 100 range, and we're still trying to figure out why. So it's pretty cool. So in addition to our illustrious event for tonight, I wanted to just mention some of the other events we found over the past 10 years. The first one is called GW150914, and this one's actually my favorite. Sorry, GW150914. So GW170817 was 2 neutron stars. It's the only example of 2 neutron stars that we have found in our data set. All of the other ones have either been 2 black holes or a black hole and a neutron star. And what's really, really unique and fascinating and amazing about 2 neutron stars versus any of the other types is that when they merge, not only do they give off gravitational waves, but they have what we call kilonova. So if you've heard the phrase supernova, right, that big explosion, neutron stars, when they merge, they also give off this massive release of energy. And we can see those with our telescopes. And boy, when we can see something in both gravitational waves and the light it gives off, we can learn a lot more about it. And so this became the most observed astronomical event in human history. We saw it in gravitational waves, which you can see in the top left. And then it's a little hard to see, but basically this is listing out all of the different parts of the light spectrum that we also observed this in, from gamma rays, X-rays, optical, infrared. We learned a whole bunch about the universe from this one event. Again, this looks advanced. Basically, what this plot is telling us is we learned a lot about how elements in the universe formed, because we think that there are certain elements that can really only be formed by neutron stars slamming into other neutron stars. And since this was our first example of seeing one, it helped us test out some of those theories. And that's the long and short of that plot. And then this one, again, don't worry about the details. We can do cool things with cosmology when we have both light and gravitational waves. I put this up here because I'm in the cosmology group in LIGO, so this plot is one of my babies. So like, I'm not expecting you all to know the details. I just put it on there for me. But it gave us a new way to do cosmology. So that was 1708-17. This one was actually very recent, GW150914. This was the most massive event we have ever seen. So it was a 137 solar mass black hole meeting a 103 solar mass black hole. And what's really interesting about this is if you look at the bottom left, there's that like gold square, and the words above it say upper mass gap. What that means is we don't think there is a way for the universe to produce black holes that are that mass from stars dying. So earlier in the talk, I mentioned how these black holes come from stars dying. There are some constraints on that. These black holes break those constraints. So we have a lot more work to do. We don't know where these black holes are coming from. They also have some spin properties that are making us question some of our astronomical theories. So yeah, this was a really cool event. And then the last one is GW25. Oh, I think I missed a number there. 250114. Yeah, I missed a 1. Sorry about that. But this was the loudest. And so what I did here was I have the signal from this event next to our original first gravitational wave. And man, you can see that intensity. It was really, really loud. When it's really loud like that, you can do things like test general relativity. You can test properties of black holes in ways we couldn't do with any of our other signals. Super, super cool. So that is where we are at today. And guess what? I lied again. There's more to this plot. So the 04 run is slated to end in October, November, soon. We are working on planning for 05. This is the tentative timeline for all 3 detectors. We are also excited because we have ideas to give it a way bigger range than we do in the 04 run. So if you've seen how much our numbers jumped from 01 through 3 to 04, imagine that next jump for 05. So we have that on the horizon. However, one thing I also wanted to mention is that the previous budget from the Office of Budget and Management proposed cutting 40% of LIGO's budget this past year. So if you like all of the cool science that I'm talking about and you think it's neat, I also wanted you all to just kind of know what's going on in our world right now. So this is a quote. This is the guy who at the NSF was like, we found gravitational waves, we did it. This is him. This is what he said about this potential budget cut. Quote, it would be nearly impossible for LIGO to recover from a cut of this magnitude. And I also did some math. Before this proposed cut, you all were paying us collectively about 7 cents a year to do all of this great science. The budget cut means you would be paying us 4 cents a year and we wouldn't have enough money to do all of this. So just to give you all some context of what we are facing specifically in LIGO, we have these plans for '05. We're trying to keep them going. But beyond that, LIGO is not the only gravitational wave detector. Just like with light, gravitational waves have a spectrum. And so LIGO and ground-based detectors are at this high frequency end. But we know there are gravitational waves at these lower frequencies. And they can see things that we can't see in LIGO. So one of the really exciting ones in this middle band that says space-based, there's a detector called LISA that is a joint project between the European Space Agency and NASA, which is supposed to fly in 2035 or so. And then at the very low end, we have these things called pulsar timing arrays. And one of the cool things about Vanderbilt here in Nashville is our department covers all of these. So this is my group where we do LIGO stuff in the stellar mass range. That's us at Topgolf. My advisor, Kron, is a very good golfer. The rest of us are not. So that's Nashville's LIGO and stellar mass community. In the middle, I couldn't find a group. The person in the middle is Kelly Holly Bockelman, who's a professor at Vanderbilt. I couldn't find a picture of the whole group, but she was on Star Talk with Neil deGrasse Tyson like last week talking about LISA. So if you are interested in learning about that space-based gravitational wave detector, I would highly recommend you just look up the last Star Talk episode and listen to Kelly talking to Neil deGrasse Tyson. I think that's a good stand-in for a group picture. And then on the other end here, there's a group at Vanderbilt called Viper. One of those folks is in the back. I'm sure he is mentioning that right now. But they do what's called pulsar timing arrays, which is a really neat thing where essentially when a gravitational wave travels through space, a pulsar is a neutron star that sends out a really, really constant signal, like it's like a boop, 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 like perfect. Like we can make our watches go based on how regular those timings are. And so if you have a network of them all out in space, gravitational wave passes through that network, and we can basically calculate the slight offset in all of those boops as the wave passes through like hundreds of pulsars and actually get a measurement for the gravitational wave signal. They actually released results and did a big NSF woohoo thing 2 years ago. Yeah, so that's pulsar timing, and that's our group at Vanderbilt that does pulsar timing. And then this is one more plot. This essentially tells you the scale of what we're looking at. So LIGO, all the stuff that I've been talking about is essentially this red part in the bottom left. And as you go up, that axis is called horizon distance. That's just a fancy way of saying how far can the detector see. And so the other thing I'll point out is that left-hand axis is not linear. So it's not like if you go up twice as much, it's twice as far. It's actually like you go up twice as much, it's like 100 times as far. And so CE and ET are two future detectors that are proposed. One's called Cosmic Explorer, one's called Einstein Telescope. They would revolutionize this science far beyond what LIGO can right now. And then that LISA mission I mentioned, that's a pretty big space on that plot. LISA has some really, really amazing range. So yeah, that's what the future holds. So you really are coming here at such an amazing time. So this is just kind of how I think of gravitational wave science up to this point. We've had about a century of work from Einstein to people trying things, failing, getting billions of dollars from the government, pulling off some amazing, amazing science. And then we got this one detection. And now we have hundreds, if not thousands of people working on these detectors. And we're right there, just after that detection, where this whole science is about to blow up. And the analogy I've been thinking about as I've been putting this last slide together is like, if you think of that detection as like the Wright brothers' first flight at Kitty Hawk, right? All of that stuff to the left, were all of the people in history being like, could humans fly? Is it possible to fly? Let me put on my wings and jump off a cliff and figure out that's not the way to do it. And then there's that one moment where we do it as humans, and it just busts the door wide open. And 10 years later, you have, planes carrying people across the Atlantic, and then we're putting people on the moon. Like, in gravitational wave science, we are a decade past that Kitty Hawk moment. So it is really exciting for us, and we're really excited to see what the future holds over the next few decades. So I will leave it there and open it up to questions.
All right, thank you, Bill.
Yeah.
So we're coming around with some microphones. We've got
Yeah.
a little time for a Q&A. Make sure that you speak into the microphone, kind of almost eat it to where we can hear you and people at home can hear you. So raise your hand high if you've got a question.
Yeah, go for it.
I'll
I'll
start,
also say
Ellie?
the questions are my favorite. So like if you're nervous, like feel free. Like I will stay literally all night and answer questions.
Thanks for your talk. It was really good. Just
Yeah.
a quick question. Do we have any idea as to the speed of these gravitational waves? Is it the speed of light?
Yes.
And do we have any idea if the speed attenuates with distance? Does it
Yeah.
decrease?
So usually I am in the habit of repeating the question, but since you have the mic, I have to remind myself I don't have to do that. So we right now believe that the gravitational waves travel at the speed of light. There are folks who speculate that they might move just a tiny bit slower than the speed of light. For reasons that I won't get into for this talk. We have tried testing that, and we don't have the precision to differentiate between the speed of light and slightly slower than the speed of light at this point. So it's a somewhat open question, but I would say right now the current consensus would be that they travel at the speed of light. Not as far as we know. So do they attenuate? So in terms of would they change speed? No. One of the neat things about gravitational waves, though, is that one of the reasons we can measure these unbelievable distance scales is because the intensity of the wave only drops off as the distance, where in a lot of other areas of physics, it drops off as the distance squared. So if you think of like gravity or magnetism, electromagnetic stuff, you have that like whatever over r squared. So if you go twice as far away, you drop off your force by 4 times. Gravitational waves don't have that squared, which means that at much further distances, they don't drop off in intensity as much. So we can see them much further out.
Two questions, actually. The first question is, these gravitational waves and the instruments you use to detect them, how do you know it's gravitational waves versus something else?
Yeah. So there's a couple of ways. The first one is we have multiple detectors. That's the big one. So one of the slides I was debating whether to put in here was a list of all of the things that we check for before we decide it's an actual gravitational wave. And I was looking at that list and being like, that's going to be like 20 minutes on its own. So yes, we check for things like geological rumblings. We have, the Richter scales. We have all sorts of sensors at all sorts of frequencies that are measuring, the vibrations in the earth and the air. And so all of the data gets filtered through that. But the main way we know that it's a gravitational wave is we see the signal at multiple detectors. And going back to the first question, because one is in, let's say, Washington State and one is in Louisiana, if gravitational waves travel at the speed of light, we would expect their offset to be like 10 milliseconds. And we see that exact delay in the signal. And so if we have a Livingston and a Hanford and a Virgo and a Cagra, and you see one signal and you do all that triangulation and it hits all of them at exactly the delay of the speed of light, and you can actually triangulate the direction it comes from. So that's the main way.
Thanks. The second question is, since you are measuring these gravitational waves from immense distances and they're going approximately the speed of light, how old are these events?
Oh, yeah. So how old are they? So doing just the quick conversion in my head, the horizon distance of the current LIGO detector would be about halfway to the Big Bang, about like 7 billion years. Yeah. So, just for context. So one of the coolest things about astronomy is time and distance are essentially the same thing. You know, when you look up at the night sky and you see a star, that star is, some millions and millions of miles away, but it also takes the light from that star, time to travel those millions of miles to your eye. And so the further away something is, you're actually seeing it further in the past. And that's true with gravitational waves. We can measure their distances. The ones that we measure further away are further in the past. What is neat astrophysically about that is we can test our stellar models that way because we have ideas about how stars form, how long they live, how many of them form in these binary systems, how many of them are massive enough to become these objects that merge, how all of that should change over cosmic time. And so we can actually then look at our distribution of distances on the gravitational wave side and say, okay, well, we're getting, these masses at these distances, which, translates to this far in the past. Does that line up with how many stars we think were forming at that time? So there's some cool connections you can do with that.
You showed the plot of the masses of the pairs of black holes colliding to produce the waves and noted that they were occurring at higher stellar masses than expected. Is that because we're not seeing the lower stellar mass collisions or because they don't exist?
So if they were lower mass, we would be seeing them. Like we know. So when I talk about the horizon distance, I'm just giving you one number, but it's actually a little more complicated than that. How far we can see is mass dependent. We can see heavier objects further out than we can see lighter objects. But we also know that, and so we can correct for that bias. And so it's not necessarily that they don't exist. It's that they don't exist. It's not that they're there and we're missing them. At least we're very confident of that. Was there more to the question than that? Okay. Yeah, because the natural next piece would be like, well, why? And it's like, well, that's what the next generation is going to figure out for us. So.
Hi. I was wondering, in between recording periods, what kind of work is going on at LIGO? Like in between 04 and 05, what sort of work will you guys be doing?
What kind of work? All sorts of work. So I'm just trying to go through the list. So one of them is the actual mirror that the laser bounces off of. So going back to the earlier question about like, how do you know it's not something else? The mirrors are some of the most precise like pendulum instruments we've ever developed, but we usually upgrade those in between the runs. The other big thing we work on is scattering. And so essentially what that means is, when I show you the video of the laser, it goes down a tube, hits a mirror, comes back. But it's not perfect. Some of the little photons in that laser are gonna, kind of shoot off in each direction and not perfectly down the tube and come back, and we call that scattering. And so that causes noise in our signal that we have to correct for. And we've come up with ways that are beyond my knowledge to control for that kind of thing. And one of the biggest upgrades between 03 and 04 was controlling for that scattering. The other big one is software. We just have gotten much better at writing good code on good high-speed computers to do these analyses in ways that we couldn't before. Part of that is machine learning. We've developed some machine learning algorithms that can do these analyses way more efficiently, or it can pull out a signal in where we wouldn't necessarily have been able to see a signal before, just because the software side is better. So that's a big one too, because you can't really upgrade your analysis software in the middle of a run, because then people are going to be like, well, the code is different, it's not one-to-one. So we have to get all of our code like approved, use that code for the run, and then when the run's over, we go back and say, okay, all the software people, do your thing.
Thank you.
Mm-hmm.
So as like technology advances in the future, would you think like astronomy would be a good career path during college, as like throughout the years?
Yeah, so astronomy is an amazing field. I think I would answer it in two ways. One is, it is a very competitive field. There are a lot of people who want to be astronomers, and a lot of them are very smart and very talented people, and there are not as many jobs in especially academic astronomy. And so it can be challenging for that reason. On the other hand, I would say that the skill sets that you gain in the discipline are very universally valuable and transferable and just even innately valuable. So, for example, ChatGPT. Who knows what GPT stands for? Anybody? So GPT stands for Generative Pre-trained Transformer. It's a type of neural network. The first time I heard that acronym GPT was in 2016, when I was chatting with a data science guy at Vanderbilt who was like, Bill, these generative pre-trained transformer models are going to be big. You should watch out for them. And like, I understood what he was talking about because I had to learn about AI and neural networks, because in astronomy, we were already using them for our research. So when all of the AI stuff hit, a lot of the folks in astronomy were like, yeah, this is kind of old news. And so for that kind of thing, like, we've always been on the cutting edge of software, big data, engineering. And so, even if you don't necessarily end up as an academic astronomer, like an astronomy professor at a university, like everyone in my program, for example, who decides to leave, they will get very, very nice jobs doing some of the most cutting edge work somewhere. So that's always very, very helpful. And the community never goes away. Like, once you're in the community, like, it's a very welcoming, open community. So like, there are a lot of people that, even if they've transitioned into more of like an industry role, like, they're still contributing to research. They're still chatting with their friends. So yeah, I would encourage anyone who's interested in the field to go into it. I always think about it too, like, if you love the field enough to spend those years studying it, it almost doesn't matter what happens after that. Yeah.
Can you hear me?
Yep. Yeah.
Sorry if you answered this, but how can you tell how far something is away? How far away the event is? Because it's not like they're all the same size. So this one's bigger, therefore it's closer. How do you know when you're judging this, like how far away something is?
Yeah. So it's not easy. So I'll give you a little peek behind the curtain if I go back to the actual waveform. So what makes gravitational waves hard is not the data, right? In other parts of astronomy, you have these massive data sets, and you just need a lot of computing power, and it scales up very fast, and it can be very hard. With something like LIGO, you could fit all of our data that we've ever taken on like a thumb drive. It's just time series. So what makes it so challenging is the analysis. And so when you actually do the like hardcore graduate school level general relativity, one of the things you learn is that you can, from the waveform, specifically how it transitions from that in spiral into that merger, how it spikes up, how that frequency changes, you can extract 14 parameters that describe that wave. one of which is the distance away that it is. 2 of the other ones are the masses. 6 of the other ones are the spins, and there's 6 of them because spin is a vector for each one. So there's 3 components for each black hole. So you get 6 spins. And then there are other things that we call extrinsic properties, which are the properties that depend on where we are relative. So where on the sky is it? Which detectors are on? Things like that. And so we run an analysis. If for those of you very advanced stats people, we run what's called an MCMC. It's a Markov chain Monte Carlo analysis. And essentially what it does is it's a program that goes through all 14 of those parameters and tests how likely all 14 of those are at a specific value and says how likely is that to match the wave we saw. And then from there, it picks another set of 14, and then it picks another set of 14. And it essentially keeps running until you hit the waveform, the numbers that give you the highest probability. And that's a very, very oversimplification of how it works. But like that's the general idea. Yeah, ask, where's the Vandy folk, the undergrads in the back? You all will have to code your own MCMC sampler at some point, so they can tell you about it when they have to do that. But yeah, that's the general idea. It's from an area of statistics called Bayesian statistics, if you're familiar. So yeah.
Let me get you one question from online.
Sure.
There was a question about if there are 2 black holes that are merging, why are they so close? And is it like because they were in colliding galaxies, or how did they get that close?
Oh, so that's a great question. So how did the black holes get so close to each other? This was an open question, actually, because we didn't know whether black holes would actually merge in the time that the universe has existed. So if we go back to Newton, I know we kind of skipped over Newton really quickly. When you think about Newtonian orbits, the Earth going around the sun, in Newtonian physics, that orbit is essentially a constant. It's stable. It doesn't decay. The Earth isn't getting closer to the sun as we go through more orbits, which is great for us. But when you graduate up to general relativity, one of the things you learn is that these gravitational waves carry energy, which means as 2 things are orbiting, they emit gravitational waves, and those gravitational waves carry energy out of the system. So the orbit actually starts to decay and they get closer. For things like the Earth and Sun, that effect is basically negligible, non-existent, does not matter for us at all. But when you have these black holes and they're this massive and they start to get closer, that gravitational wave effect actually carries off a lot of energy pretty quickly, and so the orbit actually decays faster. And when one of the things that the LIGO people, when they were trying to get funding for the detectors, had to prove to the NSF was that, yeah, all of the theory checks out that these things will actually find each other and merge. Where we think most of them come from are from binary stellar systems. So, half of the stars in the night sky are binary, which means that it's not one star, it's 2 stars, and they orbit each other. If both of them are massive enough, then when they both die, they'll both form black holes, right? And those black holes will still be in that binary orbit. So the question was, would they, at roughly these stellar binary distances, emit enough energy through their gravitational waves that their orbit would actually decay and they would come together and merge? Because if not, we could build these detectors and we won't be able to see the mergers because they're just going to be orbiting forever. But then we did the math, figured out they did, and now we have our chirps.
So if you have any remaining questions, Bill's going to be around for a little bit.
Yes, I will stay all night, I promise.
Well, I got to go home sometime.
Okay,
but
fair enough.
You can stay for a while, okay? I'd be more than happy to. But the party's not over yet because
Yes.
Bill
Cake.
brought in 2 delicious-looking cakes. We have cut them up. So if you would like either chocolate or vanilla, you are welcome to come back here and partake. And I think we've got enough for even folks to take some home. Okay,
Yeah.
so let's give Bill a big round of applause for another fantastic talk. we look forward to the 5th time him returning next year. So yeah, like I mentioned, we've got cake back here. The Seifert telescope is open. The seeing is not too terribly good, but we might get some breaks in the clouds. So you're welcome to go up there and check that out. And we're going to be back here with the cake for a while too. So if you want to go do that first and then come back get cake, or vice versa, it's totally up to you. But thank you all so much for coming this evening, and thanks to folks watching us from YouTube as well. So I hope you all have a great rest of the evening and a great weekend.